Thank you, Gary. Again, welcome everyone to our first ever ScaleX Day Zero event at KubeCon. So what's different? I mean, there have been a bunch of Day Zero events in the past. Usually, they're all technology-related events, and we've held quite a few of those. We've had networking events, NSM, which is Network Service Mesh, Day Zero events in the past. But we wanted to take a look at scale and scaling challenges holistically and talk about solutions in a very holistic manner. And we are going to look at scale today from the speakers that you see, or you just saw, as Gary pointed out, from a variety of perspectives. There's going to be talks around hardware infrastructure stacks, software infra stacks, application software, security. There are different use cases from healthcare to gaming to collaboration. And also, we'll talk about scale when it comes to hiring challenges and skill sets, because that's a critical part of the whole equation here. These are all, by the way, real-world situations, and these are not scientific papers. People have actually dealt with this, and these solutions have been deployed. These environments are brownfield in nature, which is also a very, very critical thing to think about, not a clean slate greenfield environment. And of course, the conference is only as good as the speakers. And we have an awesome set of speakers. So thank you to all of the speakers. We have Carlos and Cesar. We have Hasith and Mercian, Vinay, Anthony, Frederick, Sam, Igor, of course, Dominik. And a wonderful panel, Mark, Eli, Frederick, Sergio, Kimberly, and they have all been hosted by an ever interesting Ed. Thank you, Gary and Katie, for putting this all together. Without this, I mean, 4 weeks is just crazy. So getting all of this together in 4 weeks has been an awesome job. And finally, a big thank you to all the attendees. And just so you know, the entirety of the registration fees is going to the CNCF Diversity Scholarship Fund, which, by the way, Dan Cohn, who unfortunately passed away about 2 weeks ago at this point, he had started. So it's an awesome place. So please think about contributing, think about either in cash, kind, or personally to that fund, but it's an awesome place to contribute. I'm definitely looking forward to hearing all of the talks, and I hope you guys are as well. With that, I'll pass the ball to Dominik, who can give us a quick introduction.
Thank you, Vijoy. Good morning, everybody. Welcome to ScaleX. So today, my presentation is going to be cloud and cloud native, scalability and reliability behind the word cloud. It is all in the spirit of there is nothing more practical than a good theory before we actually dive into practice today. So I'm Dominik Tornow, I'm principal engineer at Cisco, and I focus on systems modeling. So specifically conceptual and formal modeling to support the development and the documentation of complex software systems. So the terms scalability and reliability, they may refer to different concepts depending on the domain of discourse. So scalability and reliability, they may refer to properties of an organization, or they may refer to properties of processes. But in this presentation, we'll explore scalability and reliability as properties of software systems, especially cloud and cloud native software systems. So we will begin our exploration with a rather obvious statement. Software systems shall guarantee functional correctness, scalability, and reliability. But like so often the case, that seemingly simple statement raises many hard questions. What is a software system? What is functional correctness? And what is scalability and reliability? Well, let's dive right in. What is a software system? Here, a software system is an unbounded set of processes, where processes interact by exchanging messages via a network. The behavior of a software system is the result of the behavior of the processes and the interaction between them. And the complexity of a software system is a result of the autonomy of processes and the intricacy of the interactions between them. Now, functional correctness, scalability, and reliability are properties of a software system, specifically properties of its observable behavior. What is functional correctness? Surprisingly, the simplest question is the hardest to answer. A system is functionally correct with regards to a specification if the system implements that specification. However, typically our specifications are ambiguous and at best partially complete, leading to everybody's favorite discussion: is it a feature, not a bug? Or is it maybe a bug and not a feature? But today we will leave that question to the philosophers, also known as product owners. I'm sorry, I couldn't resist. Now, what is scalability and reliability? Scalability and reliability are both defined in terms of responsiveness. And responsiveness is the ability of a system to meet its service level objectives. Now, scalability is responsiveness in the presence of load. And reliability is responsiveness in the presence of failure. Inherently, scalability and reliability are emergent properties. Neither scalability nor reliability trace back to an individual component, to an individual process. Instead, scalability and reliability trace back to a set of components, a set of processes, and their interactions. So scalability and reliability exist in between. So recall, a software system is an unbounded set of processes. Right? And as we just said, an individual process is neither scalable nor reliable, because an individual process cannot withstand an infinite amount of load, and it cannot withstand a single failure. So our task as engineers, as developers and operators, is to build scalable and reliable systems from inherently unscalable and unreliable components. Both scalability and reliability emerge from a set of components and their interactions recursively, so that in conclusion, scalability and reliability do not refer to scalability and reliability of individual system parts, but to the scalability and the reliability of the entire system. Now, how do we control, how do we guarantee emergent properties? Recall that emergent properties do not trace back to individual components. Emergent properties trace back to a set of components and their interactions. So in order to control emergent properties, we have to look beyond individual components. We have to control whole sets of components, and we have to control their interactions. Of course, anybody familiar with control systems immediately spots a familiar pattern: the control loop or the feedback loop. A controlling component or controller continuously gathers feedback from the controlled components and issues commands to the controlled components. Here, the controller is responsible to guarantee the emergent properties, to guarantee scalability and reliability, by enforcing constraints on the set of components and their interactions, so that the system can tolerate the present or forecasted load and failure. Now, wait a second. If that sounds to you like a complex description of load balancing and auto scaling, you may be onto something. Hold on to that thought. But before we go there, we go to the cloud. What is the cloud? More than a decade later, an accurate, concise, and especially a canonical definition is still not readily available. Here we define the cloud in terms of resources, resource consumers, and resource providers. So the resource consumer may acquire and release resources on demand. Resources may be anything: virtual machines, virtual switches, virtual routers, virtual hard drives, you name it. But since we define software systems as a set of unbounded processes, here in this presentation, resources are processes. So here, cloud computing refers to a resource consumer acquiring and releasing processes from a resource provider on demand. So in effect, the resource consumer requests the resource provider to run processes on their behalf. Okay, so armed with the definition of cloud systems, we may now tackle cloud-native systems. But here the situation is similar. More than 5 years later, an accurate, concise, and canonical definition is still not available. Here we define cloud-native systems in terms of scalability and reliability. Let's come full circle. Cloud-native system is a cloud system that guarantees scalability and reliability by construction. So the modifier by construction is in stark contrast to by requirement, because we speak of actual guarantees, we do not speak of mere desires. A cloud-native system is therefore a cloud system that is able to detect and mitigate load and failure. But wait, yeah, once again, anybody familiar with control systems immediately spots a familiar pattern. There is the control loop or feedback loop again. The question now, after we detect the presence of load or failure, what commands do we have at our disposal to mitigate the situation? Well, we defined a cloud system in terms of acquiring and releasing resources, or more specifically as acquiring and releasing processes. So in order to mitigate the presence of load or failure, we may acquire more resources. And in the absence of load or failure, we may release resources. So in a nutshell, we just invented redundancy. Redundancy refers to the duplication and the coordination of components to increase the scalability of a system, the reliability of a system, or ideally both. So typically when we think about redundancy, we think about the duplication of components alone. Instead of one instance of a component type, employ multiple instances of a component type. However, simply employing multiple instances of a component type does not increase scalability or reliability. The instances must be carefully coordinated to increase scalability and reliability. Again, scalability and reliability exists between components. So here, service consumer on the left, a service provider on the right, and simply duplicating the service provider does not increase scalability or reliability. Again, we have to modify the interaction of the service consumer and the service provider. We have to coordinate the duplicated components. And there are many different strategies. One example, Anycast, load balancing. In this case, a request of the service consumer may be directed to any component instance. If this strategy is applicable and warranted, Anycast may increase both scalability and reliability at the same time. Another example is partitioning. In this case, a request of the service consumer must be directed to a specific component instance responsible for that partition. Now, if this strategy is applicable and warranted, partitioning may increase scalability, but by itself does not increase reliability. And yet another example is consensus. In this case, a request of the service consumer involves all component instances. And if applicable and warranted, consensus may increase reliability, but does not increase scalability. In fact, in the context of consensus, scalability decreases as reliability increases. Okay, putting all of this together, how dare you speak of cloud-native systems, scalability and reliability? Where are the microservices? Where are the containers? Where is Kubernetes? And most of all, where is the service mesh? Okay, Let's walk through a cloud-native subsystem that is a scalable and reliable subsystem hosted on the cloud without ever mentioning a single one of these buzzwords. Okay. When we reason about subsystems, we reason about subsystems as components with an identity and an integrity. That is, an identity and clear boundaries. But if we implement that subsystem as an individual process, that subsystem may be functional correct, but is neither scalable nor reliable. We went over this. One process is not scalable or reliable because it cannot withstand an infinite amount of load, and it cannot withstand a single failure. Well, for the sake of this example, we implement this subsystem as a process group and randomly route requests between them, the anycast. Now the subsystem may withstand increased load and an increased transient failure amount. And again, for this example, we employ two different process groups. One that provides an optimal service experience, but is susceptible to a wider array of intermittent and permanent failures. And one that provides degraded service experience, but is susceptible to a narrower array of intermittent and permanent failures. So this pattern of conditional request routing is commonly known as circuit breaking. Now the subsystem may withstand increased load and an increased amount of transient, intermittent, and permanent failures. So now, on top of that, we employ autoscaling to ensure the subsystem may dynamically adapt to increased load and increased failures. But of course, now the autoscalers processes themselves cannot withstand load or failure. The situation we once again mitigate with redundancy. Some component must be responsible for routing requests, so we employ a load balancer. But there can't be any load balancer because the process groups are not created equal. We need a smart load balancer. And now the load balancer, again, a process itself cannot withstand indefinite load or a single failure. A situation we once again mitigate with redundancy. So at this point, we have a subsystem with guaranteed scalability and reliability by construction. But this picture looks much cleaner than the real world actually is. For example, this picture has you believe that there is a 2-1 relationship between autoscaler and process group, or a 2-1 relationship between load balancer and primary and backup process group. It's by no means the case. One autoscaler may be responsible for multiple process groups within a subsystem, or worse, one autoscaler may be responsible for multiple process groups across subsystems. And of course, the same is true for the load balancers. So now, as the most important slide of the entire presentation, from one point of view, a subsystem is an individual component, a component with identity and integrity. There is an identity and clear boundaries. Yet, from another point of view, a subsystem is a set of processes with complex interactions. And this diagram illustrates just how complex the interaction between processes actually may be. Here, when a consumer issues a request, that request is not simply responded to by a provider. The request itself is subject to an overall timeout, furthermore guarded by a circuit breaker. First, the system tries up to 3 times to load balance the request across a primary process group in order to get optimal service experience. And if that fails, and if the overall timeout did not trigger yet, the system will try once to load balance the request across a backup process group to get a response, albeit with a degraded service experience. Again, this diagram alone illustrates that we cannot simply consider an individual process or a group of processes. We also have to consider the interaction between the processes involved to see scalability and reliability emerge. Now, to the conclusion. Scalability and reliability. Scalability, that was defined as responsiveness in the presence of load. And reliability is responsiveness in the presence of failure. Both scalability and reliability are emergent properties. They do not track back to individual components. They track back to a set of components and their interactions. We define cloud systems in terms of resource providers and resource consumers that acquire, and the resource provider acquires or releases resources from the resource consumer on demand. And then we define cloud native systems as systems with guaranteed scalability and reliability. All cloud native systems, as they have to control the emergent properties of scalability and reliability, are control systems. And scalability and reliability are guaranteed by our Leatherman tool, redundancy, the one-trick pony of scalable and reliable engineering. With that, we put an end to theory, unless somebody does have any theoretical questions, and then we jump right into the practice. Thank you very much.
Thank you, Dominik. Do we have any questions from our attendees? Go ahead and put the question in the Q&A chat window, or you can raise your hand and we can unmute you. All right, Dominik, thank you very much for the presentation. We're actually staying right on schedule, which is great news. And with that, excuse me, I'm going to introduce our second presentation of the day.